I mean, you were 1 minute probably when we were started discussing the silicon cavity that was realized between GILA and PTB.
Okay, do you hear me well now?
Yes.
Good. Okay, so the point of that is that this is a way of reducing the thermal noise, but you're still limited by the thermal noise in these systems. And that means that after a couple of seconds, this frequency starts to drift. Luckily, second scale is about the time scale of atomic clocks. So that's about the time it takes to prepare and then interrogate the atoms in your systems. But that also means that there's some bandwidth limitation at the Hertz level to these atom reference signals. And this is not a big issue for long-term timekeeping. But if you're interested in efficient timekeeping also on the short time scale, or if you're interested in quantum sensors that rely on these atoms for references, then it can be very interesting to have higher bandwidth in your system. Some mitigation techniques to the issue of Dick effect, which is aliasing of your clock laser noise onto higher timescales, can be used by using multiple atomic ensembles. So this is also related to what Luca Pese talked about yesterday, or non-destructive measurements that Daniel Benedicto mentioned yesterday as well. Okay, so in an active optical clock, the clock laser itself has a line width dictated by some narrow atomic transition. So this is this in itself means that you can use some clock transition to define a very narrow natural line width of your laser. The cavity stability fluctuations can be suppressed quite a bit by going to this bad cavity regime that I already talked about. And finally, this atom reference signal is no longer something that's bandwidth limited, but it's continuously generated. So you actually have very, very good temporal resolution if you want to use this system as a quantum sensor. Okay, so Superradiant basics. If we look at just a simple model of a two-level atom, you can have some decay from the excited to the ground state at a decay rate gamma, giving you this exponential function. But if you have two atoms that are in some way that I'll come back to indistinguishable, then you can actually have an increased decay rate to gamma, and any sort of increased decay rate basically is termed superradiance. If you have a decreased decay rate instead, then you can get subradiance. And initially, this doesn't look great. If we have atoms that decay faster, that typically would mean that the Fourier limitation causes us to have a broader line. So it doesn't off the bat sound like a good thing. Typically for clocks, you want very narrow transitions that are very long-lived. So making those transitions short-lived doesn't sound great, but let's come back to that in a moment. So for these two atoms, they need to be indistinguishable with respect to the field, the radiation mode that they're coupling into. So if you have atoms that are separated a lot in compared to the radiation wavelength, then the small phase jitter will have very large effects. So you don't get any coherent emission between them. You just get them behaving like individual atoms. Rather, if you have them very, very close to each other, much closer than a wavelength, then it's hard to distinguish what atom is actually emitting, and you get this increased radiation by 2 gamma. So in the 2 atom case, we can set up the energy levels of such a system here. So if we have full excitation, we're in this doubly excited state, and we can be in the doubly ground state. But if we have a single excitation in the system, we have these two degenerate superposition states. One is an antisymmetric and one is a symmetric state. And what happens then is that it's not possible to make a transition from the fully symmetric excited state to the antisymmetric state. So instead you have an enhanced decay rate to the symmetrical superposition state and further down to the ground state. And this is the source of the superradiance. So if you generalize this to n atoms, then you can go to the decay model. I won't take you through too many of the particulars of the decay model. Just the overall scheme is basically the same as when you just have two atoms. You can have a fully excited or a fully ground state, and basically any superposition states in between those will have a rather large level of degeneracy. This means that the radiation is again enhanced, but rather than just having something that's faster decaying, you actually get this cascading effect that accelerates. So you get an emitted intensity that looks something like this. You start out with all atoms in the excited state, you start out with the expected initial intensity, but then as you cascade down these many degenerate levels, you get a peak in the output that scales as the square of the number of atoms. And an essential part of this decay model is that you can write up your Hamiltonian with a collective spin operator rather than individual spin operators that you have to sum over. Okay, so leaving superradiance for a very short while, we look at cavity enhanced coupling. So when we talk about lasers, the cavity is very essential, and two important numbers show up there. So the atom couples to the cavity mode with some coupling factor G, and the buildup of coherence in this system can be characterized by the cooperativity C0, which basically is given by the coupling factor to the radiation mode, and inverse proportional to the decays of the system. So the spontaneous decay to 4 pi and the decay rate of the cavity mode kappa through the mirrors. This means that the coupling of the atom into the cavity mode is modified to the Purcell rate rather than gamma, which is the free space decay rate. Depending on the value of your cooperativity, that means that you can either enhance coupling into this cavity mode, or you can suppress it if you have a cooperativity that's much smaller than 1. And systems like this are typically described by the well-known Jaynes-Cummings model, with the first term that describes the cavity field evolution, the atomic evolution, and then this coupling between the atom and cavity, where we've taken the rotating wave approximation. Now we start to fill up the cavity with a lot of atoms here. And this means that we can talk about a collective cooperativity rather than a single atom cooperativity. The collective cooperativity is proportional to the total dipole moment, if you will, of all the atoms inside the cavity. So in the decay model, we required that atoms were much closer than lambda. But if we want to talk about optical clocks, then it's very hard to fulfill this requirement. Instead, we're going to work in a regime where the distance between the atoms is much larger than lambda. And that sets requirements either to the position of the atoms. If they're in a very well-defined pattern, or in a very well-defined geometry, this can still generate superradiance. Or if you have them inside of a cavity, where you get this collective coupling that allows you to build up coherence in the system, basically. So the requirement that we need to look for is that the buildup of coherence in the system is much larger than the decoherence we have in the system. So what do we do if we want to investigate a little bit the dynamics of a superradiant laser? Well, if we went back to just having a few atoms, we could do a full quantum model. But typically we want to have a large number of atoms to actually get any appreciable output power in this system. Especially if we use very narrow transitions, like for example the millihertz transition in strontium. It's not a lot of photons that would be emitted if we just had a few atoms in the system, even if they were re-excited once they had emitted light. And the equations of motion to describe this scale exponentially with the atom number. So instead, there are two different approaches. Either you can regard the atoms as identical and use this collective spin operator inherent to the Dicke model, and a kind of a collective dipole moment as well. Or you can consider many unidentical atoms. In that case, you need to generalize the James-Cummings model to this Tavis-Cummings model, where you basically sum over the values of all the different atoms, all the different couplings, and all the different spin operators. This second model is very important if you want to be able to consider position and velocity and finite temperature of the atoms. Whereas the first model is a very good approximation as long as you have strongly confined atoms in lattices. Now, there have been recently some realizations of superradiance that's interesting for clock purposes. Superradiance is by no means a new phenomenon. Dicke published his paper in '54, and in the '80s especially, there was a vast amount of publications on superradiant lasers and superradiant systems, but never at that time, obviously, in cold atom systems. So cold atom systems is only something that we've had access to more recently, and lately, within the last 10 years or so, there's been a lot of interest in trying to make superradiant lasers on these narrow clock transitions in cold atoms. So here's a system of calcium atoms. Calcium has a nice transition that has a line width of 400 hertz. And they realized these very nice pulses emitted out of the system, where depending on the atom number, they can see this decay in pulse height. Similar results were obtained for the much more narrow millihertz transition, strontium 87. Again, you see these beautifully shaped pulses that are very similar to the one shown over here. And this quadratic scaling they show down here of the peak emitted photons with the atom number. And notice here that the atom number is in the 100,000s. And then this nice Bloch sphere picture that I'll return to in a bit shows you the evolution throughout the pulse as the Bloch vector goes from fully excited and cascades down to the fully ground state. In this system, they also, while remaining in a pulse laser, they actually showed clock operation. So because the pulses here are hundreds of milliseconds long, this is actually comparable to normal optical atomic clocks. And so they get pretty quite nice stabilities in the 10 to the minus 16 range. There's also realizations on strontium-88. Strontium-88, the very narrow clock transition is not accessible unless you have large magnetic fields, but the 7.5 kilohertz line is a bit more easily accessible. So in the group of Hidetoshi Katori, they made experiments inside hollow core fibers, and at the University of Copenhagen, we've made some with atoms that are not confined in lattices, but rather are just thermally expanding inside of an optical cavity. So this is the optical cavity that we used at the University of Copenhagen with a sample of atoms fluorescing in the blue mott down here. And the atoms are about 5 millikelvin, so they're quite hot compared to cold atom systems. But conversely, we have about 10 to the 7 to 10 to the 8 atoms in our system. We use this Tavis-Cummings model that I showed you previously in order to model the system, and that means that we can really get the full behavior of the spatial extent of the atomic ensemble and the velocity distribution of the atoms and how that influences the coupling parameter to the cavity. So here I show on the left-hand side simulations and on the right-hand side experimental observations. And we can directly compare these two and see that they agree very well. We have a pretty good understanding of what's going on in our system. So we pumped our atoms, was just pump them coherently with a pi pulse at the time of the green dots here. Then after about 2 to 5 microseconds delay, we see this peak in the emission pulse in bright yellow here. And as time goes on, we see oscillations, some slight oscillations happening. And if we detune the cavity away from atom resonance, we can sharply enhance the oscillations that are going on as the excitation in the system is kind of sloshing back and forth between cavity mode excitation and atomic excitation. This signal, this plot over here shows the spectral behavior of the system. So because the atoms are quite hot, we're not truly deep in this bad cavity regime that we would like to be in. Our system is kind of a hybrid system where the single atoms are in the bad cavity regime, in that it's a 7.5 kilohertz line width on about 600 kilohertz cavity resonance, but the ensemble as a whole is in the bad cavity regime. But we still see here we have a laser pulse with some oscillations afterwards, and that creates a beat signal, and we can do a cumulative investigation of the spectrum, how that develops as time goes on, and we see that the spectral density is kind of pulled towards atom resonance. So we do have some suppression of the cavity pulling of the laser frequency. And here we again plot this spectrum along the x-axis, and then we see for all different cavity detunings along the y-axis that the spectral density then as we move around in time develops. So this is at the peak of the primary pulse, and then as we evolve in time and have subsequent oscillations, the spectrum kind of splits up into these two branches, with now a primary branch with high spectral density that has a reduced sensitivity to the cavity pulling. Okay, so most of, or everything what I've shown you so far is relying on pulsed operation, but we would like to have continuous operation for this to be a nice atomic clock system. So the question is, how do we sustain emission? now we can return to this block sphere picture, and rather than thinking about this as a single atom that's excited or in ground state, we're thinking about the ensemble as a whole. The cavity means that if atoms decay into the cavity mode, it's very hard for us, or impossible for us, to distinguish which atom actually emitted that one photon. And so we can view them as effectively one large dipole. So as the dipole starts to decay towards from the north to the south pole, we reach the peak of the emission right around equator. Right around equator is also where we're maximally sensitive to the phase of the system. And one of the primary advantages of a superradiant laser is this the fact that it's the atoms rather than the cavity that stores the phase coherence, right? So this is the idea that the cavity is no longer the frequency filter of the system, because it's not the cavity that stores the coherence. It's not a system that relies on vast amounts of light inside the cavity stimulating emission from atoms. Rather, it's atoms collectively decaying and sending light into a bad cavity, which means that mode quickly decays to the surroundings. So we want to somehow extend the duration of this fall from the top to the bottom. And we actually want to extend it in such a way that we become stationary more or less and stay right about here over the top of the equator. So this is not something we can do for a single atom, but for the ensemble as a whole, this is actually possible to do. It could be done via repumping, or it could be done by swapping in and out individual atoms. So repumping is what you typically do in a laser, but the problem is that it generates heating. Generating heating is not a big issue in most conventional lasers, but if your laser relies on optically trapped ultra-cold atoms in lattices, then this is a big issue. If you have sharp restraints on how your atoms can move along the cavity axis, then this is also an issue. So the different approach of swapping out the atoms is a bit more promising. This way you can discard atoms that have already decayed into the ground state and fill up the cavity with new atoms already in the excited state that then quickly synchronizes with the atomic ensemble that's already inside the cavity mode. What performance can we expect from a continuously operating system? This was already predicted by a couple of different groups. This paper from 2009, the group of Murray Holland, shows for the millihertz line in strontium 87 that you can actually reach optimal pumping rates with a requirement of about 100,000 to 1,000,000 atoms, and in that regime reach millihertz line width of your laser as well. So this is comparable, line width comparable to the decay rate of the atoms. But it's actually limited by, the line width of this laser is actually limited, as I mentioned earlier, by the per cell rate. So this is entirely dependent on the parameters of your cavity. Now, disadvantage of this system as I alluded to previously, is that it relies on quite few atoms that are not very willing to decay. So that means that the powers, as shown here, for example, are in the picowatt regime. So it's very little power that you get out of this cavity, out of this laser. Here, a couple of calculations from Claus Mølmer in Aarhus are shown on the millihertz line and on the kilohertz line in strontium. Both show this initial limitation at the per cell rate, which is the blue dashed line here. But then due to other effects that I won't really get into now, you can, for high atom numbers on the kilohertz line, for example, you can actually enter a regime where you go below this per cell rate. But that requires very high flux. So down here on the x-axis, they both have plotted the pumping rate or the flux, depending on what scheme you use. So this is a repumping of the system, of the collective dipole, basically. Here are some realizations by the James K. Thompson's group again, where they actually realize quasi-continuous operation. So they do this by repumping the atoms inside optical lattices. This first one is on rubidium. So here we're cheating a little bit in the sense that we're actually in this decay regime with atomic spacing much smaller than the wavelength. But they get sustained superradiant emission for many, many milliseconds by repumping, and finally they deplete the sample because of heating in the system. And you can then optimize your repumping rate to sit in the right place on the Bloch sphere, and at the same time have the optimum number of photons in the system. And here on the 7.5 kilohertz line, they use this repumping scheme shown over here. So going from the ground state to actually one of the Zeeman levels of this 3p1 state, and then up to the states that are typically used for repumping. So this gives you kind of a 4-level laser scheme with some leakage holes that can be plugged. Again, they see sustained superradiant emission here for about 400 microseconds, which is much longer than the pulse length of a few microseconds. But once more, they lose their atoms due to heating. Disadvantage of strontium is that repumping, because it's kind of a leaky scheme, requires quite a lot of photons on average to do a single repumping. So instead, you could go this route of trying to refill the cavity. And there are some proposals, but there haven't actually been any good realizations yet. So there's a lot of groups working on this. One approach to that is either a sequential coupling of sequential loading of atomic bunches into an optical cavity mode, or kind of a continuous conveyor belt of atoms into a moving optical lattice cavity. And after this talk, there'll be the poster session where there's a poster on this kind of system. Alternatively, there's the approach of taking a thermal beam. So there are two different papers on this, where this proposal is basically having an oven very close to a cavity and just blasting the atoms directly through the cavity. This means that you get a lot of atoms that are way too fast and don't interact, but you get an exceedingly high number of atoms, so you can actually get a decent output power. And by decent output power, I don't mean milliwatts. I mean that you can up it to a level of nanowatts rather than the picowatts I showed you before. Okay, so with that, I'd like to finish off. I hope I've shown you that Superradiant lasers can generate this narrow line with light from atomic clock transitions, these narrow clock transitions. One of the big advantages is this cavity noise suppression that we can achieve in the bad cavity regime. And you could do that by continuously feeding atoms through a cavity with either this conveyor belt or oven. Those are some of the most intriguing approaches at the moment. And then I didn't finish my last sentence here, I see. But this is going to say that it promises interesting applications for quantum sensors with high bandwidth as well, and very fast atomic clocks that can achieve high accuracy and high stability very fast compared to traditional methods. Okay, thank you for listening.
Thank you, Stefan, for the very, very clear and interesting presentation of the Superradiant laser. So, would like to know if there are some questions. Please raise your hand or write in the question and answer box. In the meanwhile, while the other people are thinking about the question, I have a question for you. The Superradiant laser for somehow is quite similar to the classical hydrogen maser, where you are also in the same cavity regime. Can you comment on why in the hydrogen maser you have a problem of threshold for having the emission, while in the Superradiant laser you don't have, it seems that you don't have any problem of threshold for achieving the Superradiant regime? I mean, in the maser, either you have enough gain in the system, or the emission is incoherent, and you are not able to establish a coherent between the various microwave photons that are emitted, while here in the Superradiant laser, you don't have this problem.
I would say you still have this problem in the Superradiant laser. There's a very clear lasing threshold, at least for the pulsed case, the experiments that I showed earlier. So here, for example, if we look at this plot here, the atom number on the x-axis here, if we decrease the atom number enough, we don't have the coherence buildup that we need. So here we've shown a lasing threshold at about 2^10⁷ atoms in our mod. So there's definitely a threshold. Maybe the reason why it gives the impression that there's not much of a threshold is that these very narrow line with atoms, the incoherent light that they emit is very weak, right? Because when they just emit light incoherently into 4π, there's not a lot of light coming out. And even if that is incidentally into the cavity mode, it could be even less light. So I mentioned that the Purcell rate, the rate at which individual independent atoms couple into the cavity mode, scales as with this single atom, here with this single atom cooperativity. And in our experiments in Copenhagen, for example, the single atom cooperativity is on the order of 10⁻⁴. So that means that we actually suppress the radiation, the spontaneous decay from the atoms into the cavity mode quite heavily compared to 4π. But if we have enough atoms in there and increase above the lasing threshold, then the collective emission can still be quite strong in this pulse because it's collected over such short time. So I think the behavior is still there, but we're just in a regime where the difference is so much more extreme between actually having emitted light and not having any.
Thank you. Do we have some other question for the audience? I don't see any hand raised. So maybe Rob, you want to introduce, I want to thank Stefan for, again, for his talk. And I leave the stage to Rob that will introduce the next session, the poster session.
Thank you very much, Filippo, and thank you to both our speakers today. I enjoyed very much both of the talks. Our next session starts in 10 minutes at 4 o'clock, and this will be a poster session. There's two parts to this session. One is a Zoom session like this now, where all of the poster presenters will have a chance very briefly to introduce themselves and to tell us why we should go and have a look at their posters. And also a session online where the posters are displayed and you have a chance to connect to and chat to each of the individual poster presenters. I'll put up in the main chat now the link to the Zoom session that will start at 10 o'clock, where each of the poster presenters will have a chance to introduce themselves. So I invite you to join me back here in 10 minutes on Zoom via this link I just sent you, which you should also have in an email sent around by Mercedes to join for that poster session. And I would ask all of the poster presenters to join immediately so that we can prepare that session well beforehand. I see there's a question quickly from Vijay.
Sure.
Vijay, would you like to ask your question directly?
Yes, please.
Please, we can hear you.
Yeah. Yes.
Go ahead, Vijay.
Yeah, actually, I am not presenting poster. Sorry.
Okay, so then join in the link that I just sent at the Zoom session.
Yeah. Yeah.
I look forward to seeing everyone there at 4 o'clock. Thank you both for your talks today, and thank you to everyone for attending the two talks, and Filippo for chairing the session.
Thank you.
We shall see you in 10 minutes.